Very well. So we define, let us rewrite the definitions here. Reflexive relation, symmetric relation, and a transitive relation. A relation like R on set A is called one, reflexive if for every element in A, X is in relation with itself. Symmetric if X is in relation with Y, then you can conclude Y is in relation with X. We say that it's transitive if X is in relation with Y and Y is in relation with Z, then you can conclude that X is in relation with Z. Example. In this example, we're going to define a relation which we call equality. Define a relation like R on real number set. Real numbers. We define this relation this way. For all real numbers, like X and Y.
Professor, the mic is, it's blurry.
X is in relation with Y if and only if X is equal to Y. We want to investigate to see if this relation, which we define as equality, is reflexive, symmetric, or transitive. Okay, this relation that is defined as equality is actually reflexive, symmetric, and transitive. It is reflexive. Why is that? Because for any number, that number is always in relation with itself through R. Why is that? Because every number is equal to itself. It's just true for every number. So this is reflexive. What about symmetric? In algebra, we learned that if we have two terms, two statements equal to each other, it means that it doesn't matter you read it from left to right or right to left, we always have equality for any two numbers, X and Y. If X is in relation with Y, for sure you can say that Y is in relation with X. If X is equal to Y, if two terms are equal to each other, it doesn't matter if you read it from left to right or right to left. We can switch the order. And of course, it is transitive. In algebra, again, we learned that if X is in relation with Y and Y is in relation with Z, then for sure you can say that X is in relation with Z. This relation is equality. X is equal to Y and Y is equal to Z. Of course, you can say that X is equal to Z. X, Y, and Z, they are all real values, real numbers. A relation that is reflexive, symmetric, and transitive is called an equivalence relation. Equivalence relation is reflexive, symmetric, and transitive. So equality on real numbers is an equivalence relation. Well, what do you think about this relation? So we define a relation like R on real numbers this way. We say that for all real numbers like X and Y, we define the relation X is in relation with Y if and only if X is less than Y. Is this reflexive? Is this symmetric? Or is it transitive? Very well. Thank you, everyone. So, of course, this is not reflexive. For example, 1 is not less than 1. This is not true. Is it symmetric? It's not symmetric. 1 is less than 2, but 2 is not less than 1. So it's not symmetric. What about transitive? Of course it is transitive. If X is less than Y and Y is less than Z, for sure we can conclude that X is less than Z. So this is only transitive. So this is not an equivalence relation. Perfect. So we can define a relation this way. We're going to define relation T and Z. Congruence mod proof. Define a relation like T and Z. Remember that Z is the set of all integers. This way, for all integers, X and Y, we can use M and N. M is in relation with N, if and only if. Three divides their difference. Or M is congruent N mod 3. So these two definitions are equivalent to each other. Is it symmetric? Is it reflexive? So write down reflexive first. Reflexive, symmetric, transitive, which one is that? So this is actually an equivalence relation. Why is that? So to show that it's reflexive, we need to show that for every integer, that integer is in relation with itself through T. It means that for any integer, like M, 3 divides M minus M. But we know that it is true. 3 divides 0. 0 can be written as 3 times 0. This is always true. Symmetric, it says that, hey, if 3 divides M minus N, you should be able to conclude that 3 divides N minus M as well. So if 3 divides M minus N, we should be able to conclude that 3 divides N minus M as well. Well, what's the definition? 3 is a factor of m minus n. It means that there is an integer like k such that m minus n is equal to 3k. It means that if I just multiply both sides by negative sign, I get n minus m equals to 3 times negative k. It means that 3 divides n minus m. So this is true. How about being transitive? It says, hey, if 3 divides m minus n and 3 divides n minus another integer like l, then you can conclude that 3 divides m minus l. How do we prove that? Using the direct definition. 3 divides m minus n, it means that there is an integer like k sub 1 such that m minus n is equal to 3 times k sub 1. 3 divides n minus l, it means that there is another integer like k sub 2 in z such that n minus l is equal to 3 times k sub 2. What I'm going to do, I'm going to add these together. If I add these two, I get m minus l equals to 3 times k1 plus k2. This is another integer. It means that 3 divides the difference between m and l. So this is also true. So this relation is an equivalence relation. Perfect. The definition. Well, remember we talked about partition on a set. Well, we're going to use a partition and define a relation on that set. Definition. Given a partition on set A, so suppose we have a partition on set A.
Professor, it's not focusing again. Or just did.
So suppose we have a partition on set A. The relation induced by the partition is defined this way. So we say that for all x and y in set A, x is in relation with y. We define that relation as R if and only if there is a set in that partition like A sub I in the partition such that x and y both are in AI. how did we define a partition? We said that, hey, suppose we have a set like A, then there are subsets A1, A2, these are non-empty subsets, A3, A4, A5, and so on, such that they are disjoint from each other. And if we take their union, the union is equal to set A. Is equal to set A. I and J's. If you have a partition for a set, remember that we used Z and we used the quotient remainder theorem to show that we have partitions, different partitions for set Z. Now we say that, hey, if we have a partition on set A, the relation induced by that partition is defined this way. For all members in A, we say that X is in relation with Y if and only if you can find one subset, like A sub I, such that X and Y are members of that partition. For example, take set A to be set including 0, 1, 2, and 3. Let's include 4 as well. And suppose we have a partition this way. The partition is defined as these subsets: 0, 3, 4, and we have 1, and we have 2. Question says, find the relation R induced by this partition. Very well. So remember that a relation is a collection of ordered pairs. What ordered pairs? We say that X and Y is in relation R if and only if X can be connected to Y using R. That's how we build a relation. So can you say that 0 and 0 is in this relation? Can you have one subset, one of these subsets that actually include 0? So remember that set A is divided into these subsets. These are the subsets that you have: 0, 3, 4, 1, and 2. This set has 3 subsets. They have no element in common. They are mutually disjoint. And if you take the union of these elements, it's equal to A. Given a partition on set A, the relation induced by the partition is defined this way: X and Y in A, X is in relation with Y if and only if you can find a set like A sub I such that X and Y are in AI. Well, can we say that 0 is in relation with 0? Can we say that 0 is in relation with 3? Can we say that 0 is in relation with 4? Are they all members of one set? Of course. Can we say that 3 is in relation with 4? Can we say that 4 is in relation with 3? Yes, of course. They are all belongs to one set. Of course, you can connect them together. 1, 0, 3, and 4. So far, we have R equals to 0 and 0, 3 and, let me write the whole thing, 0 and 3, 3 and 0, 0 and 4, 4 and 0, 3 and 4, 4 and 3. So here you have 3 and 0, and here you have 4 and 0. What about this partition? Can you say that 2 is in relation with 2? Of course. 2 is a member of this set, of course. What about this one? Can you say that 1 is in relation with itself? Yes. 1 is in relation with 1. So this is the relation that we have. This is our relation. Then if the question says, hey, check to see if this relation is reflexive, symmetric, transitive, we move on to the next step to check those properties. But first, we need to define the relation. How do we define the relation? We need to check to see which elements are in relation with each other, which elements are members of one set. The rest of the elements, 3 and 3, 4 and 4. 3 is in relation with 3, 4 is in relation with 4. Now the question is, do we have a reflexive, symmetric, and transitive relation or not? The theorem says the relation that is induced by partition is actually gives us an equivalence relation. Theorem. So the relation induced by the partition R on set A is an equivalence relation. It's reflexive, symmetric, and it is transitive. There's a note for you. Note. Congruence mod D is an equivalence relation. So, for example, we say that M is in relation with N if and only if M is congruent N mod D. What's the meaning of that? It means that D divides the difference between M and N. So to show that it's reflexive, it means that for any number like M, D divides M minus M, or D divides 0, or 0 is equal to D times 0, which is always true. To show that it's symmetric, if D divides M minus N, then we should be able to conclude that D divides N minus N. So using the definition, it means that M minus N can be written as dk k is an integer. So if we multiply both sides by negative sign, we get n minus m equals to d times negative k, which means that d divides the difference between n and m, which is always true. Then to be transitive, if d divides m minus n and d divides n minus l, we should be able to conclude that d divides m minus l. Again, by using the direct definition, here we have an integer like k sub 1 such that m minus n is equal to d times k1. D divides n minus l, it means that we can find another integer k2 such that n minus l is equal to d k sub 2. Adding these two together, it gives us m minus l equals to d times k1 plus k2. It means that d divides the difference between m and